guys, welcome for this part. And so far we have discussed about the work done in or finding the work done when we have the constant force. Now we're going to use or apply this concept in finding it out the work done by the variable force. What exactly is the variable force? That is a force which is dependent on the position, and in details we're going to see in this part. Now, work done by a variable force. Let's see. Now, first of all, what exactly is a variable force? Variable force is that kind of force which changes its direction or its magnitude with the position. Or let me give you the example that what we have done in the introduction. So in the introduction what we had two kinds of slope, that is a uniform slope and the bunny slope, somewhat, or the non-uniform slope, somewhat like this. So we have found it out that this, let's say this is an angle theta. So we have found it out that if the sphere will going to move in this direction, so under the gravity, so it will have g sine theta as the acceleration. But now for this case, if the sphere is at this position, theta will be different with the horizontal, and if the sphere will be at this position, theta will be then different. If sphere will be at this position, then also theta will be different. When we compare all these positions, theta at these positions will be different from each other. So therefore different acceleration, or therefore different force. So what we can say that with the position the force is now changing. So what we can say that the work done by such a force for an infinitesimal displacement is given by dw is equals to f vector dot ds. That means for infinitesimal displacement, what do we consider? That force is not changing so distinctly. That means there is no such big variation of force for a very infinitesimal displacement. So therefore, for the total work done from going from, let's say, from A to B, let's say this is position A or this is position B, or let's check it out what exactly. So this is the given figure to. So in this, it is moving from A to B. Now we have to find out the total work done. So the total work done going from A to B is f dot ds. Going from A to B, it's f cos theta. So at any moment we are considering that it is making an angle theta with the displacement. That means force. This is the force which is acting on the particle. So at any moment we are considering that this force is making an angle theta with the displacement. So in terms of rectangular component, we can write this f vector as fx I cap, fy j cap plus fz k cap. And ds can be, in general, ds can be written as dx I cap plus dy j cap plus dz k cap. So therefore, after substituting it for the complete work done, that is the integration from f dot ds from A to B, we'll get fx dx plus fy dy plus fz dz. Now what we can say that for the first term, as we can see that it's only fx dx. That means force is along the general force. Now for this first term, force is only along x direction and displacement is also along x direction. So therefore we'll take the limit only from xa to xb. That is what exactly is the displacement along x direction. Similarly, this goes for y and z. That means for the second and third term, we'll take the limits, that is ya to yb. This is ya actually. This is ya to yb, za to zb. Now the example for this is that a spring force, or the spring. That means what exactly is there? We know that the spring exerts a force proportional to its displacement, but with a negative sign, because directly proportional to displacement, but with a negative sign, because when we'll extend when there is an extension in the spring applies the force along or opposite to that. when there is a compression in the spring, then spring also applies force again opposite to that. So this is being this we can see it from the figure that this is the spring where you have the natural length, that means there is no extension. Now after displacement, force of spring is along this direction and you have applied, or the extension is along this direction. This is what exactly is showing that F is equals to minus kx. So therefore what we can see that the spring exerts a force proportional to its displacement from equilibrium F equals to minus kx, and where k is a constant and minus sign is due to the spring forces opposite to the direction of the displacement. Now we have to find out the work done by the spring force. Now we have to find out the work done by the spring force. By spring force. Okay, so what do we know? That the force which spring applies, the magnitude of that force is equals to kx. This is what we know. Now if we consider the situation that somewhat like this, if we consider the situation that spring is, let's say this is the spring with us, and now this is the natural length of the spring, and let's say that this natural length is L. This natural length means that at this position spring is at equilibrium position, that means spring does not apply any force, or it is relaxed, it is in the relaxed position. Now let's say it is being extended by applying some force, something like this. Now this extension is, let's say this is x initial. Let's consider that this is the x initial, xi. So let's this as xi. Now after that, let's consider that spring is now extended more and it goes to x final. So let's consider that this displacement is x final. Let us denote it by xf. This shows that this is x final. Now since displacement is along, if we consider that this is y-axis and this is x-axis, so displacement dx is, let's consider, because since force is a position dependent, that means depends upon x, so let's consider that dx, so dx as the displacement or the infinite similar displacement. So this dx will be along plus x direction because displacement is along x direction. So what we can write, so therefore we can write work done is equals to integration f vector dot dx vector. Now what do I know? That if spring is being extended, so force will be this will comes out to be kx. This is the magnitude part, and dx magnitude into cos 180 degree, because the force is acting in this direction and displacement is acting in this direction. So therefore cos 180 degree. So what we'll get? We'll get this as minus integration kx dx. So what exactly we are finding it out? We are finding it out, let's say this is the configuration A, this is configuration B. Let's say the spring is in the configuration A and now it has been extended to configuration B. So what exactly the case is that spring has initial extension as xi and now it has the final extension as xf. So therefore what will be the work done by the spring force in going from configuration A to configuration B? So what exactly? So limits will be for the x, that is the x initial to x final. So what we're going to get? We're going to get this as 1 by 2 with a minus sign k x square with limits as x initial to x final. So what we're going to get? This we're going to get. So complete total work done by the spring force will comes out to be minus k x final square minus x initial square. This is what we'll get. So depending upon the situation, that whether xf is greater than xi greater than xf, or xi is equals to xf. So when we have xf greater than xi, so work done will comes out to be negative. When we have x initial greater than x final, so work done by spring force will be positive. When we have this as the equal, so work done for this case will comes out to be none other than 0. So let's see the example. Now force, a position dependent force F vector is given to us as 7 minus 2x plus 3x square Newton. This is what it is given to us. Acts on a small object of mass 2 kg. Mass is given to us as 2 kgs. Now displacement is given to us as x initial is 0 and x final is 5. So what we have to find out, work done in joules. That means what exactly? Work done is equals to going from x initial to x final is equals to F dot dx. Since the displacement is along x direction, so we are taking it as F dot dx. So this force is acting on the body to displace it, so therefore the angle between the two will be 0. So what we can write this as simply F dx, from x equal to 0 to x equal to 5. So therefore this will comes out to be 7 minus 2x plus 3x square dx with integration x equals to 0 to x equals to 5. So what exactly we're going to get this as 7x minus 2x square divided by 2 plus 3x cube divided by 3 with the limits as 0 to 5. So we're going to get, after substituting the limits, we're going to get 7 into 5, that is 35 minus 25 plus 125. So therefore this is the total work done and this will comes out to be 135 joules. So the option D is correct for this. So now let's proceed. Now, which of the following are the equivalent units for the spring constant K? Now, what do we know about the spring constant? F is equals to Kx, Kx or minus Kx. For the spring constant, the minus sign doesn't matter because we have to find out the unit. So let's consider the magnitude as F equal to Kx. So since we know that the unit for force is Newton and displacement is meters, so this is K meter, so the unit for this will comes out to be Newton per meter. So option A cannot be there because it's Newton meter square. Now let's find it out. Work done is equals to half kx square. Work done is equals to half kx square. So for this case we can say that work done is in joules and x is in meter, so this will comes out to be joule per meter square, K. So we can say that option 3 is correct for this. So therefore the second, let's check it out about second. So what do we know about Newton? Newton is equals to kg meter per second square. Now we got this as unit of K as Newton per meter. So this will comes out to be kg per second square. Kg per second square. So therefore this one is also wrong, kg per meter square. So therefore option B, which option C is correct. Option only 3. Yes, this is the only one, that is a joule per meter square. Now let's check it out the other example. Now in the next example, the particle moves under the effect of force that is equals to Cx. Now x equals to this, from x equals to 0 to x equals to x1. Now what will be the work done? So it's simple. It is instead of given as f equals to kx, it is given as cx, and this force, so this force is, body is moving under this effect, body is moving under the effect of this force. So displacement, I mean the vector or the angle between the force and the displacement vector will be 0. So what we can write that f equals to integration f dx. So therefore this will comes out to be cx dx from x equals to 0 to x equals to x1. So this will comes out to be half c x square with its limits 0 to x1. So this will comes out to be half c x1 square. So therefore according to this, option B must be correct. So guys, what we have learned what is a variable force and how can we find out the work done by the variable force, and we also have seen that what exactly or how to tackle the problems including when we have the variable force. So now let's proceed for the next part.